Yep, we're good.
All right. You guys see my screen?
Yeah.
Okay. So so for the VAR paper, just kind of a quick overview. Um, so previously people said, hey, LLMs, they work great. Let's try just doing autoregressive on images. And um, you can do this at the pixel level, you can do this at the patch level. And the most obvious first thing you might do is just raster order. So I'm going to start in the top left corner. I'm going to go across the top and then keep going. Um, and you can imagine that this is great because there's a natural sequencing for language, but for images it feels a little wrong, right? Because if you're in the middle of the image, then your context is all the pixels above you, but you have no context for the pixels below you, right? Um, and so what the VAR paper is going to suggest is that if you go from low res to high res, then this provides a natural, a good inductive bias. And so this is just my overview slide. Obviously, we'll get into the details of how they do all this. But so that's the big change is rather than just switching from raster order to spiral to space filling curve, those all still fundamentally have the problem that when you're halfway done, half of the pixels are in your context, but half the pixels are not. Okay. Whereas if you go from low res to high res, then what you say is all of the pixels, but only at a low res, are in my context. And then, so eventually we'll get global features like it's a picture of a dog. And so then you'll have the background is blue sky above, green grass below, no high frequency fine details. You'll just have like, you know, that high level stuff. And so in order to implement this, what they used is they use variational autoencoders, and actually they use vector quantization. So it's VQVAE. And they purposefully decided to use a GPT-2-like LLM, which actually I think is one of the strengths of the paper, is that they didn't go for the best possible transformer architecture. They said, we want to show that what worked was the low to high scale technique, not what worked was we had a really awesome transformer. Okay, they did make a few changes to like the normalization and stuff, but they tried not to just say like, let me get the best. And one of the consequences when you go from the way they did low scale to high scale is if I'm at a medium scale and I'm going to predict the medium high scale image, that medium high scale image is multiple tokens. So even though we are now still going left to right linearly, we're not going one token at a time. We're actually going to go multiple tokens at a time. And again, this is just the overview, so the details we'll see in a minute. So I'll pause just to see if there's any burning questions before we get into the details, how they do this. All right.
Yeah, I'm trying to explain VAE for those who are newer to the concepts in the
I have a slide on it,
really?
although
Oh,
you can explain there because it's just one slide. It's not really
yeah,
explaining
yeah.
in any detail.
It helps with images.
Yeah, yeah. Okay. So again, I think I kind of covered this, but you can imagine. So we have LLMs, and the diagram from the paper says, yeah, here we have this nice clear ordering. The cat sat by, blah blah blah. And you could take an image, you could break it into these 9, and then if you go in raster order, then you go 1, 2, 3, 4, 5, right? So again, the problem is when you've seen 1, 2, 3, 4, 5, and you're predicting 6, patch 6, then patch 3 is in your context, and so you can say, okay, yeah, but you don't have patch 8 in your context, and that's a little bit unnatural, right? And you can change the ordering, like I said, but any 1D sequence is still going to fundamentally have this problem. So what they say is that let's have lower res, higher res images, and now there's sort of a logical ordering. So you could see at what they call R3 here, maybe you can't tell that it's a bird, a parrot at this point. If you knew it was a parrot and I asked you, is the parrot facing to the right or the left? At R3, you could probably say, yeah, I think this is the beak, and so I think it's facing to my right. Okay. And so you can imagine that at R4, you're getting this global context. You know, what color is the main body of the bird? It's probably blue, right? There are things that you can learn. It's not working out the fine details. And so then as you keep going, more and more local information is available. And so now if you're actually trying to predict specific pixels on a portion of the beak, you have from this, you have a lot of more local context in addition to just the general global context about this. So this is a nice concept, but it still begs the question, how do we actually implement this idea of going from low scale to high res scale? By the way, just stop at any point and ask questions. I can try to monitor the chat, but it's not always easy when I'm screen sharing. So I apologize. Either somebody else give a shout if there's a good question in the chat that I'm missing.
I have a question here. Hello.
Yeah.
What I'm really I'm not sure. I can understand what is a token in an image in a sentence, but what would be a token in an image? Is some pixels, because you can have like lots of different. It's would be a really huge dictionary.
It's the perfect question. That's the perfect question. Okay. I have this idea that I want to go from low scale to high res. What the heck is a token? How do I tokenize this? What are the pieces? So that's the what we need to get into next. That's the solution that we need to solve. This is just a high level description, but it doesn't actually make it obvious at all how you pull this off. So perfect question. Okay. So a couple concepts that we're going to use in order to explain the tokenization scheme. Okay. So one is autoencoder, right? So here we have a simple autoencoder, and you take an image, you pass it through some CNN layers, you have a bottleneck in the middle, and this can be considered your embedding. This is a deterministic embedding. So you can't use a simple autoencoder as a generator. Okay. So we have variational autoencoders, which then take the input, and you may have CNN layers and whatnot up front, but ultimately, instead of getting a single embedding, what you're doing is you're creating a probability distribution. Okay, so generally speaking, what we're doing is we're transforming it to something simple. And so here we have, in this slide, it's a Gaussian, multi-dimensional Gaussian distribution with diagonal covariance. Okay, and what we want is we want the encoder to basically transform our data distribution into this simple Gaussian distribution, which we know how to sample from. And then when we do generation, the real power of this variational autoencoder is that the decoder knows how to do the reverse transform, basically to take something sampled from this multidimensional Gaussian and put it into the data distribution. So I don't know, this is all I have. I wasn't really covering VAEs in this, so if you want to add any color about VAEs.
It looks like Anton's giving, people are talking about VQVAEs, but my understanding stops at VAE. And the only thing I'd add is that this is basically what led to latent diffusion.
Yeah, so VAEs were used for image generation standalone, I don't know how many years ago, right? Like 4 years ago or whatever. And they weren't very good. At the time, they were very interesting, but ultimately you got some blurry images, and you can do things to clean up the fact that the images are blurry. So then, yes, next we're going to go to vector quantization, because VAEs, actually, if I go back, this latent vector that you sample is continuous. Okay, so if we say the dimensionality here is 256, you have 256 floats, they're continuous, real valued. All right, so for anything where we're going to do a GPT style thing, we need a vocabulary, we need a discrete distribution. So we're going to use vector quantization, and the way I describe vector quantization is it is just a multi-dimensional version of rounding or quantization. And so super quickly, if I said you have floating point numbers between 0, 1, and round it to the nearest hundredth, okay, you'd create 100 buckets, and basically, right, we know how. You just, like, at the 100th place, you truncate the rest of it, and you drop things into the buckets. So that would just be very simple rounding into 100 equal-sized buckets. But if I said to you, hey, my data is actually not distributed uniformly. Let's say it's somehow whatever, like heights of people, and it's kind of bell curve shaped, right? But I want good use of my buckets. I want my buckets to have roughly equal numbers of people in them. Then one thing you might do is you might have narrow buckets near the middle and wider buckets at the ends. And if you do it right, then what you'll wind up with is, once you see your data, you'll get approximately 1% of the people falling in every bucket. So that's going from just simple rounding to uneven sized buckets. Then the last thing you could do is you could say, rather than predetermining those, I'm actually going to get some data, and I'm just going to learn. I'm going to see, based on that data, how I should apportion my buckets in order to have them all be roughly equal samples. So good. So now we just basically have a learned 100 bucket thing for one-dimensional data. How do you do that for multi-dimensional data? Well, if you have a vector of length 256, you just do the exact same thing that you were doing in the one-dimensional case, except you use, let's say, L2 loss in order to figure out which bucket you're closest to. And then you just shift the buckets around until you get roughly equal numbers in every bucket. So for me, I just say that vector quantization is just learned rounding on multidimensional vectors. And then for me, I have the mental intuition for it's not something super fancy or anything like that. Yeah, I see a raised hand.
Yeah, I have a question. So the basic question, I think it's also being asked in the chat window, is why do we have to go towards vector quantization? Because one of the reasons for actually doing a VAE is that you have a continuous distribution, so that a subtle change in the input will lead to a subtle change in the output, as opposed to any kind of dramatic changes. Whereas once you move into the quantization world, you lose that subtlety, the proportional change, a benefit that you actually get from VAEs.
I don't know if I can answer the question fully. I'm not the author of the paper, but what I will say is that if we want to use a GPT style transformer, we are going to have a fixed vocabulary. And so we want to discretize this. If you're familiar with like Whisper or these other audio models, what they do is they do residual vector quantization. And so you vector quantize, and there is this rounding error that you're losing information. So then what you can do is you can take the error between the original and the and your first quantization, and then you can quantize that error. Okay. Yeah. And then you can take the leftover from that. You do that 4 times, and now you've actually got a much more accurate approximation of your original than if you just did 1 round of quantization. And so we'll see that they don't explicitly use residual vector quantization in the VAR paper, but the process they use ends up imitating that. As they go through the scales from low to high res, they are doing residuals, and so it ends up kind of being like RVQ.
Got it. Thank you. And one other question while I'm still here. Would you be able to make this presentation available to me or to us? So that
yeah. I have a PDF on GitHub. I can share the link.
Great, thanks.
Yeah, so again, if you just think that this is just multidimensional rounding such that we get equal numbers in every bucket so that we're making good use of our buckets, then what do we call the list of buckets? Right, if you use equal size buckets, then you just have a formula for calculating the buckets. But if you are now learning them, you have to just write them down. You have to store them somewhere. And so by convention, the list of the buckets is called a code book. Okay, and rather than super fancy buckets, I think what they do is they just store the center of the bucket, the centroid, or whatever you want to call it. And so then you're not actually like defining the upper and lower bound of the bucket everywhere. You're just saying, here's the middle of the bucket, here's the middle of that bucket. And then when you want to quantize something, what you do is you actually compare it to every bucket, and you see which has the lowest L2 distance, and then that's the bucket that you quantize it to. That's the one that you round it to. So it is, I don't know, slightly expensive. So if you have 4,096 buckets, it is like order 4,096 to quantize something. You have to compare it to every one of those, and then you say, yeah, it was closest to bucket 17, so I'm now going to throw it in bucket 17. All right. So now that we kind of have a little bit of information on VAEs and VQVAEs, so now the question is, how do we tokenize? How do we fit images into an LLM? Okay. And so the solution in the VAR paper is we're going to break the image into patches, and each patch is going to go through our vector quantizer, our VQVAE. But what we're going to do is, if it's a low res image, we're going to give it fewer patches. And if it's a high res image, we're going to give it more patches. Specifically in the VAR paper, they worked on ImageNet, 256 by 256 color images for ImageNet. And they said the high res in their case is 16 by 16, 256 patches. And the lowest res is 1 patch. So low res is very, very low res. It would really just be like the average color of the entire image, right? Just the mean. So that's like extremely, extremely low res. And if you think about it, the 16 by 16 is actually not that high, but it's a small image. It's only 256 by 256 image. Okay, so they actually sped it up a little bit. They didn't use every single possible size in between, but so you have a 1 by 1 is your lowest res, then a 2 by 2, and then a 3 by 3, and then a 4 by 4. And then at some point they got to like, 8, and they jumped to 10, and then they jumped to 12 and whatever. But that's not like the schedule they used is not particularly important. If you just did it naively, you would say, I have 16 steps from 1 to 16. They had, I believe, 10 steps if you look at the code in that VAR paper. All right. So basically that means that the lowest res image is going to get 1 token as its embedding, and the token ID is just the bucket number from our vector quantizer, right? So I was saying, if you compare it to all 4,096 and 17 is the closest one, then literally what you do is you just say 17 is my token number, and then GPT-2, right? It goes through the embedding layer that turns it into a dense vector. It goes through however many, was it 12? I don't remember if they even use GPT-2, small, medium, whatever. It goes through 12 transformer layers, and then out pops your next token prediction. You guys all know LLMs, right? So basically, the bottom point here is normally our LLM is predicting the next token, but if we're predicting the next higher resolution, now that's multiple patches. So when I start with just 1 patch, I'm going to predict the next image, which means I'm actually predicting 4 tokens at once. And then when I have that one, I have the first and the second one, I have 5 tokens in my context. I'm now going to predict the next 9 tokens all at once. And then when I have 14 tokens in my context, I'm going to predict the next 16 tokens all at once. Okay. And basically what you can do is if you just change the shape of your autoregressive mask, instead of being purely diagonal, you have it be kind of block diagonal, then what you can do is you can say, when I have 5 tokens in my context and I'm predicting 9 more, so what is that, 6 through 14 or something like that? I'm going to change my mask so that tokens 7 through 14 can still only see the first 5. They cannot see token 6. Okay, so tokens 6 through 14 all have equal amount of keys that they can attend to, equal amount of information. the fact that they are ordered in a particular order gives them no extra information because we are creating the mask, slightly blockwise so that, yes, in fact, the very last token, the 14th token, still can only attend to tokens 1 through 5. It cannot see any of the earlier tokens from its level. Okay. And then in practice, what we do is, if you're familiar with pre-fill versus decoding, right? In the pre-fill stage, we are inferencing multiple positions at once. Here, there's no reason not to do that as well. You could do them one at a time, but it would just be less efficient. But that's just an implementation issue, okay? Whether you inference the 9 tokens one at a time or you do them all at once, because of the attention mask, it's exactly the same. All right. So now the thing we're going to do is we're going to modify our vector quantizer a little bit, and we're not going to just use a vanilla VQVAE. There's a special VQVAE that was trained specifically for VAR. Ultimately, they tried it both ways. They said, I will just take this image, and when I want low res, they just did linear interpolation. Okay, there's nothing fancy here, whether you're using like the CV2 function or the PyTorch built-in function. It's literally just linear interpolation. So I start with my image. When I want a 1 by 1, you just basically say resize or linear interpolate down to 1 by 1, and it gives you the average. And if you say 2 by 2, it's just the simple thing. So there's no fancy learning going on here. So they tried it where they said, I'm just going to do 1 by 1, 2 by 2, 3 by 3, so on and so forth. And every one of those, I'm going to run my patches through the vector quantizer. It worked. What they found worked a little bit better, however, is after you have the 1 by 1, you can project that back to your full size image, 256 by 256. And of course, it's a little bit more complicated, but you can imagine that you're then just going to get a solid color for the whole thing because you only have one data point. So when you upscale that, you're just going to get this flat uniform thing. What they do is they say for the 2 by 2, instead of also predicting the original image, I'm going to subtract what the 1 by 1 predicted my full image was going to be. I'm going to subtract. So if you have this mean color that you've predicted, I'm going to subtract that from the image. And that's what I'm actually going to predict for that's what I'm going to use, what I'm going to quantize for my 2 by 2. So this is where the part I mentioned earlier about it's a little bit like residual vector quantization. All right. So then after you have a 2 by 2 that's been vector quantized, you then upscale that back to 256, subtract that from what you have. And so you're successively doing this. So when they did it in 10 steps, what it means is that the last step, that's the 16 by 16 patches, they're not predicting the original image. They're predicting the leftover after all the previous 9 quantizations have done their job. Okay, and so you can imagine, like, now you're really getting into, I'm just predicting fine details. I'm looking at the chat numbers going up, and I apologize if I should be answering questions or if you guys are just super chatty, but I'm like 44 freaking messages.
Is active. If it's important, someone will interrupt, but chat's always
Okay.
It's a
Okay,
question on
thanks.
positional encoding, which is always fun for images.
I don't
What kind of
actually
positional-
remember what they did for positional encodings off the top of my head. Sorry. I could go look at the paper real quick. But yes, there have to be positional encodings because the attention is position invariant.
I think you mentioned that in the last step, they're predicting the deltas from the previous step, right? I wonder,
Yeah.
do you have an intuition of why a VQVAE would work better here as opposed to a residual VAE? Because it seems like residual would work better with predicting residuals, but I don't know.
I'm not familiar with what you're saying, residual VAE.
Yeah.
I mean, the idea here is that you have the VAE, but in this case, we're quantizing it, okay? And so so you have two forms of error, so to speak. You have the fact that you have downscaled this a lot, okay? And then you upscale it back, and so then you've lost a lot of information there. And then the other error you have is the fact that when you downscaled it, you then quantized it, so you moved it a little bit, and then you upscaled that sucker that you moved back.
Yep.
So so I don't know how to answer your question because I don't know that other residual VAE, but I can tell you that what they're doing is the combination of those two errors is what the next iteration is then trying to encode. Okay.
Gotcha.
And,
Thank you.
And so the 2x2 is going to downscale, quantize, have those both kinds of errors created when you upscale that back. And then the 3x3 is going to just look at the leftover errors from both levels 1 and 2. And then the 4x4 is going to look at the leftover errors after those 3, and so on and so forth. So so this VQVAE, one of the key things though is that the code book used when you do level 1 versus the last level, the 16x16, it's using the exact same code book. So I've seen different people ask, you potentially could have a more accurate quantizer if you use customized code books for the 1x1 level versus the 16x16 level. But since we want to feed all of these into our same GPT model, that's why we're forced to use same code book for all the different levels. And so basically then the VQVAE, when it's learning its code book, has to decide on codes that work well both at the high res and at the low res end. It has to come up with some sort of compromise because these codes are going to be shared everywhere. In my head, my intuition is that even though the code book has to be shared and it may not be optimized for low and high res, still what's happening is you're going to get these broad global features at lower resolutions. You're going to get the sort of low frequency information encoded. And as you get to the last end, that's where the high frequency features. So the details of the grass, you know, the texture of the fur, that's going to not happen until probably quite late in the quantization process. And so this next slide, I wasn't planning on spending a lot of time on it, but what you can see just from this algorithm is that you input an image and it's going to loop, in this case 10 times, doesn't matter if it's 10 or 16 times, going from the 1x1 up to the 16x16. And the key thing though is that they have this queue that they're sticking on, but you get all of those embeddings at the different layers at once. This is not like a separate kind of a thing. You do the multi-resolution quantization in one fell swoop. You get all the resolutions simultaneously after you've run your for loop. Okay, so it's a package deal. Okay, so this is a dedicated multi-scale VQVAE that gives you all your resolutions at once, and then reconstruction also has to be an iterative process. You cannot say, let me do the reconstruction at the 8x8 level without the information about the other ones, because this is a residual process. You have to have all the earlier ones, and then you sum all the predictions from all the earlier ones with your predictions in order to get your final prediction. It's just like in an LLM, you couldn't say what is the output of just the 8th layer, right? It's a residual stream, so you have to have layers 1 through 7 in order to know what the output of the 8th, or I didn't say that quite right. What's the residual stream after the 8th layer? You can say what the output of just the 8th layer is, but you can't say what's the residual stream after the 8th layer unless you also have the first 7 layers. So it's the same thing here. You can't say what's the 8th resolution unless you also have the first 7. All right, so just to clarify what the training process looks like is the multi-scale VQVAE is trained separately. So you, in this case, it was ImageNet. So you give it a bunch of ImageNet and it tries to encode these images in a way that when they're decoded, the L2 loss is the lowest. And it's going to do this as best it can, and then it's going to be frozen. So the actual LLM part did not involve any of this training. At this point, this sucker is completely frozen. Then what we do is we say, given a fixed VQVAE, I'm now going to train my actual LLM on this idea of I'm going to give it one patch, it's going to predict 4. I'm going to give it 1 + 4 patches, it's going to predict 9, then it's going to predict 16, then it's going to predict 25, up until at the very end, for the 16 by 16, it has all the context of all of the earlier resolutions, and it's going to predict 256 tokens in one fell swoop. So in this case, it was trained on ImageNet. And so if you're wondering for the very beginning of the process, what is the prompt? There's one token that encodes the class. So there's 1,000 classes in ImageNet. And so I don't remember, I think it was embedded, but basically, so you start with a class token and it predicts the 1 by 1. And then you have the class plus 1 by 1 and it predicts the 2 by 2, and then so on and so forth. And this repeats until you get the final, the 256 tokens. And then for your actual image, you need to sum up all of this and have the decoder turn that into pixel values, because this is still a very special VQVAE, and you still need the decoder part here. So all of this stuff that's happening with the multiple scales, this is all happening in latent space. This is not predicting pixels. This is predicting latents. Okay, so when we have tokens that are embedding from our VQVAE vocabulary, these are all vocabularies in the latent space. And that's pretty much it. So then you can see some of the results here, and they had really good image quality. If you guys are familiar with FID, distance inception score. And then they also said, because we were able to do inference in chunks, we actually had many fewer steps than if you did autoregression naively. So if you did one patch at a time, you would have 256 inference steps. They had 10 inference steps, going from 1 to 16 by 16 in just 10 steps. Maybe those individual steps were a little bit more expensive each, maybe not. I haven't really done the math. But you can imagine that 10 inference steps is still going to be a lot cheaper than 256 inference steps. And I think, they also talked a little bit about scaling. So if you look at some of these other models, the performance improves as they get bigger, and then they sort of hit a wall. And in this case, they said, yeah, ours didn't hit a wall. They didn't really run this over a very large number of orders of magnitude. So it's still TBD whether or not, as you really get bigger. I don't blame them for not having the resources. They're not a Google, okay? But nevertheless, the fact that it didn't hit the wall is good, but it's not really proved yet until you really get to probably more like 7 billion parameter scale or something like that. But if you compare, for example, DIT, if you looked at these first 3 data points, you'd like, yeah, this thing scales great. And then you get the fourth data point, and it just fundamentally architecturally hits a wall. Okay, so they're saying VAR hasn't hit a wall, but we still don't know that it's not going to hit a wall on the next data point. You know, you really have to, right? So the ultimate proof is in the pudding. Until you try to build a GPT-4 size thing or whatever, you know, you just don't know whether or not you're going to hit a wall. For images, maybe it's not GPT-4 size, but it's the same concept that it's good to be asking that question, but I just don't think that they quite did it over a large enough spread. Some sample images, and here, if you look, you can see this is left is earlier in training, right is later in training, and this is scaling up the size of the LLM that they used inside VAR. And so obviously the bigger LLM does better. And then I don't know that early in training is really that important, but it does learn better. And so late in training, it does better quality images. That's not surprising. So to conclude, the key things that they're selling us on, why they think this paper is good, why they think this technology is good, is that it's fast. It's much faster than autoregression in more naive ways. It generates very high quality images, and they say that it has the right inductive bias. That going from low scale to high scale, there is a very clear 1D ordering. Nobody would argue that somehow medium res should come before low res. Everyone's going to agree on the inductive bias. Whether or not that inductive bias proves to encapsulate everything that we need, I would not have necessarily guessed before GPT-2 that next token prediction was sufficient to be able to generate really complex, mathematical proofs or something like that, right? So I don't have the ability to guess whether or not low res to high res is enough information for it to be able to do whatever. But because it has a very, intuitive inductive bias, then it does mean that you can do in painting, you can do out painting, you can fill in any direction with a fixed autoregressive patch order. You can't. If you do raster scan and you give it just the bottom of the image and you tell it fill in the top of the image, it can't do that. It can only go from top to bottom. So this one, because of the way it works, it can go in any direction, in, out, mask, whatever. So ByteDance did share the code here, and they have 2 follow-up papers that are that I've seen. Maybe there's more. They had an infinity paper. They did video. They've also done. This was just ImageNet. Now they've done text to image, like that's a pretty obvious thing. And there's a XAR instead of VAR paper now, where they generalized, instead of just scale, they say you can have arbitrary precedents. And then they also added some stuff that I haven't quite worked my way through, where they're matching as what seems like a little carrot on top of the autoregressive learning to make the image quality even better. One other thing I have, if you're reading the cheat sheet, there's a lot of terminology, and so I did, if you're reading the paper, there's a lot of terminology, and so I did actually make a cheat sheet. I'll share the link to the PDF, but so basically they have images, and then they talk about their F, and you're doing this on individual patches at individual scales. And so then you have your tokens here that are these cues, which combined all the cues together make an image R, or rather a latent R at a given resolution. And then when you're decoding, then you go back and you get your F hats, and eventually you get your image hat. So that's useful. All right, so I don't know if you guys want to ask me questions or if there's other discussion you guys want to have.
I mean, first off, thank you. I mean, it's great that you volunteered in the last minute and helped charted this this entire session. And also, thanks for the PDF file. It looks all the slides look amazing. I'm just thinking in terms of, does it even make sense to think or rationalize VAR against how diffusion models work? Is that going to help me? Because some of these are rat hole things that I don't want to get into, but do you think in your, based on your experience, does it help to understand or rationalize VAR by comparing it against diffusion models? Because even in the diffusion models, you have a sense of resolution increments that you see as in practice, although behind the scenes, the thing that is driving is actually the differential equations.
I think there's one thing that I think personally is a very important trend from VAR, and that's the idea of predicting multiple tokens at once. When we do next token prediction, we're sort of fixing the information content per step. Okay, and for me, if you have words like the and whatever, there's not a lot of information content there. But if you're processing code, or you're processing like what is 12 times 15 or whatever, and you're outputting digits or something like that, there's like really high information density, and you cannot get it slightly wrong or you're just dead. And so whether it's scaling up or scaling down or whatever, but this idea that we can have variable information content. So I think the byte latent paper from Meta, and then and to a certain extent the large concept model, for me, one of the things that they all these papers have in common is that they're addressing the idea that the information content may not be uniform token by token by token. And so I think that the idea that maybe if we're doing reasoning or doing other things, that we can embed things with multiple tokens, that allows us to get more information content into one inference step. And so I think there's a huge opportunity to either make transformers faster, language models faster, or have reasoning better if they have certain capabilities to dial up and down. So I think the idea of predicting multiple tokens at once, I think there will be a lot of successful research playing with that. The XAR paper already says that maybe scale is not the one and only way to do it, but they are looking at this idea. And so diffusion has like really strong mathematical foundations, but we know that transformers are just really full. So there's no reason why like the transformer can't learn the score function that diffusion models are learning. The real question, which I don't know, is just kind of who can do it in the fewest steps. But it seems like if a diffusion model using a UNet or replacing the UNet with a transformer can learn the score function, then if you gave it something similar, a progression of images, then you should be able to learn that same score function using attention. So yeah, so I think that this is something to pay attention to, but not necessarily that it has to be literally just the scale technique that these guys used. But yeah, I would pay attention to this idea of that multiple people are approaching of changing around our tokenization, whether it's byte latent, LCM, this, or something like that.
So there
But
was a
to answer, sorry, just to answer the question more directly, though, at least my understanding, whether there's something to take away from this for whether understanding diffusion helps. I think, to me, this is an example of an earlier paper. Both diffusion and this approach of scale prediction is an example of an earlier paper. I think it's by Sutskever, where the idea is you actually don't need to solve an ODE or something. If you can train a model to denoise for an arbitrary corruption, either adding Gaussian noise, or maybe in this case, you can interpret the next scale like downsampling prediction as a corruption, where you actually think of it backwards. You have a high resolution image and you've corrupted it by sampling it down, and you're trying to predict backwards. Like all of these are viable ways to think about the image generation process. So in this case, it's a combination of using an LLM for attention, for being able to predict the next scale rather than raster scan, plus the fact that you need some sort of tokenization to actually use the LLM in the first place. Other than that, it's kind of similar, and it seems to work really well.
Yeah, thanks.
Regarding that point of multi-token prediction, Meta put out a paper last year about training LLMs with multiple tokens. They did it during training and not inference. And then they mentioned in Llama 3 that they use this technique. In TED, basically all your points there for sample efficiency are like spot on. They go into that. In terms of at inference time, this is kind of what motivated a lot of the work behind speculative decoding. So speculative decoding is kind of multi-token prediction with a small model. And that idea came out of research that, they started off with let's just predict multiple tokens and see how that goes. And that led down to the path of some speculative decoding.
Nice.
I have a question on the training time of this one. So this approach seems clearly very fast at inference time because it can predict so many tokens in parallel. But did they put any mention in on how long it takes to train something also in comparison, for example, to diffusion models?
That's a great question. I don't remember them discussing that in the paper.
So
or maybe I just didn't pay close attention.
these are actually a lot bigger models than diffusion models, and their inference is a lot slower. So like you try 4.0 image generation, it takes on the order of 15, 20 seconds, and it's significantly larger. The big thing with autoregressive generation is you kind of scale up a lot more than you do with diffusion, right? We have really small local diffusion models. Like your iPhone locally can do Genmoji diffusion, but autoregressive models just at base layer, they're larger than diffusion models. Now, the inference tricks of like, LCM LoRa, where you can skip a bunch of steps for diffusion, those haven't been super applied to image generation, right? So VARs for autoregressive image generation don't have speculative decoding yet. Or maybe they do, but there's a lot of inference optimization that hasn't hit yet. So there's room to grow, but base level, we expect diffusion models to stay small. Autoregressive models kind of get big as they generalize. And yeah, there's a lot of inference optimization that hasn't hit yet.
Yeah, I think that the optimization is a key point that Vibo shared, right? So you compare this to like the very first diffusion models, they were doing, I don't remember, either hundreds or thousands of steps. And we've dramatically improved that. And so if this is a useful technique, then you would expect that there's going to be a bunch of optimizations, improvements upon it. This is just day one.
As a minor point, I guess, you mentioned 4.0 image generation being slow. I'm actually not sure whether so they're clearly doing VAR, but I'm not sure they're doing the same VAR, because you can imagine that if you want to do text to image or sort of this kind of multimodal thing, you want to actually fine tune your text model to actually intake the same tokens and learn, like teach it to do the task all with one model rather than doing it with separate models. So it could be that is the reason. Like if you just had a dedicated VAR model, you can imagine it being pretty good.
Anyway. I have a question about this actually, and I think we had a short thread in Discord about this. It doesn't really seem practical to like completely jointly train one model. Like, if you have the sort of 4.0 architecture or something like that, it probably has to be just a post-training thing, right? And then, so you need some way to integrate that with like the separate like VAR architecture that you've already trained. And I think RJ in Discord, I'm not sure if he's here, had a plausible explanation that like you have some reserve token that you use to like delineate the image tokens from the text tokens. And then the only thing you need to do in like post training is like the chat model needs to learn to like say, okay, now this is an image or something. And then it gives you text tokens and you take the text tokens and you have a text conditional VAR and that generates the image or something like that, which kind of pencils out to me, but I'm very curious practically how they do something like that.
I don't know. I think you could do it with tool use like you're describing, but people fine tune on tasks all the time. When they, for example, you want to add like a tabular or like a numeric modality or like an image modality to a language model. You do your pre-training on a big like text corpus, and then you have a much smaller like modality corpus that you sort of train your encoder to do the quantization so that you can actually have a image token, but then you sort of fine tune your model to understand image tokens and text tokens all in the same sequence. So then you don't actually need to do co-train everything. It is like a post-training thing. And you hope that you don't lose the text capability when you gain the image capability. But I think Apple has a bunch of papers on basically anything to anything prediction. Like I think it's called like 4M or something. I don't know how well it works, but
Meta has a the segment anything, then there's another one that's 6 modalities in one: audio, video, depth. Meta also has Chameleon, which is native training, so separate than like Lava. They have a native image language model. I guess Apple might too, but if there's a modality.
Yeah, I'm thinking of the 4M series of papers, which I think is Apple. But again, I don't know how well it works. Anyway, I don't know how anything works in practice at these scales. But yeah, that's my guess.
Yeah. Regardless, you need some sort of like tool use thing to like say, okay, now this is an image, right? And then you generate the image tokens, and then you like end the image and keep generating text or something like that, or whatever.
But
that right?
But you may need that just for the UI, essentially. The LLM model may not care. And whether you use tool use to sort of dispatch to a new model, that's clear how it used to work, because you could basically trick one model into the generating some description that then would fail downstream. But if it's all one model, it's all in the same space, and that allows you to do image understanding, whereas previously, like, these models didn't understand what was in the image that they generated themselves. So that's maybe a way to check whether, like, if you ask to generate an image of like a tech bro with and say no glasses and it generates glasses, you can ask it whether it contains glasses.
Yeah. No, that's an and I'm sure it does know that.
Yeah. And also just moving this into a different track of conversation. In the case of diffusion models, lots of things have evolved, like there are control nets and LoRa's and image prompts and whatnot. I wonder what would happen in this world, in this universe, to get that kind of control. Because I work in the movie industry, and one of the things that we actually care a lot about is consistency, like character consistencies and so on. And control nets are the current way of dealing with all of that. So do you know if there is any literature around VARs along those lines?
I don't think there's any literature yet, but like OpenAI, they let you refine the image, and there's clear character consistency when you do multi-step refinement of your image. So it seems like they've definitely had that in mind.
Yeah, they actually call that out in the blog post they have about the 4.0 image capability, and I think what I recall is that they claim that that's because of this autoregressive nature of it, right? So you have the history so that the attention can pay attention to the previous image, so you kind of get it for free. That was my interpretation of what they were saying.
Yeah, then this suggests that it is one model, and that's cool. Or I guess it could be one chained model.
Yeah. No, I guess so. My point in the Discord was actually that it's unclear to me whether there are reserve tokens that it's trained on in post training, or if they're just reusing the text tokens but with some sort of special token to say, okay, now I'm generating an image, and then now I'm not generating an image. But like, I don't think it matters too much, but you might like lose less of the text capability if you use reserve tokens.
Yeah, if I had to bet, that I would bet on them using reserve tokens, because you don't need that many. It's a pretty small vocabulary on your code book, and exactly your point. You don't want any forgetting.
Yeah, I don't. Well, normally you don't reuse tokens. Well, I was not aware that people do reuse tokens ever. You just you have your dictionary for text tokens, and then you have your implicit dictionary through your encoder that you use, your VQVAE, that is now your image dictionary, and they're like, they don't overlap. So yeah, you just use those, and your model learns to sort of naturally use whatever it needs.
Yeah, I think there were some early multimodal LLMs where you had like a beginning, image token, and then you reuse the same space. But yeah, I think we're all saying the same thing, that that's probably not the conventional wisdom now. Is just use separate tokens, and then you can have whatever, hypothetically, just an orthogonal corner of your embedding space.
Yeah, but those tokens, I totally agree. Those tokens are delimiting tokens. For example, when you train an LLM model for fill in the middle tasks, even though it can only generate one way, right? You use like you add new tokens that say like, now you're doing the fill in the middle task, and here's the beginning and here's the end, and now start generating the whole, essentially. You create new tokens for those delimiters, but the vocabulary that it like learns to use the right vocabulary.
Cool. Thank you so much, Ted, for stepping in. We were just gonna casual discuss. Slides are always appreciated. And good to see you here. For next week, anyone have a topic they want to discuss? They want to volunteer? They want someone else to volunteer? They want to do half a paper?
I want someone to volunteer the stuff that just came out of Anthropic on
Okay, I might do that since I've done the other three. So unless someone else wants to do it, I'll do the fourth one.
Awesome.
Okay. I might get someone from Anthropic to join us. We'll see. Otherwise, next week is Anthropic. If anyone hasn't seen my favorite meme, Matthew Berman, he said, this is the most surprised he's ever been, but he was just as surprised in the thumbnail as always. It's very sad, very sad. We have a running Discord of all his thumbnails. But okay, I'll share.
I'm gonna make the thumbnail for this YouTube. Okay, good. All right, we got the thumbnail.
Cool. Thanks, guys. See you next week. And thank you, Ted.
Thank you, Ted.
Thank you, Ted.
Thank you.